Greetings, Mr. Sutton here, bringing you the AB Calculus 4-5 Extra Practice number 6 solutions on points of inflection. For this problem, we're given the point 0, -2 on the curve C and also the first derivative, 4x over 9y. We want to know which of these statements is going to be true. So these are all talking about having relative mins or maxes and the reasons behind it. In all the reasons, they state that the first derivative is 0. So I think if we plug in 0 and -2 into this curve, we're going to get 0. And we do. 4 times 0 over 9 times -2 is going to be 0. But the real question is, do we have a min or a max, and is it because the second derivative is positive or negative? So we can definitely eliminate a few of these right off the bat. If you have a positive second derivative, that would give you a relative min. So this choice down here about having a relative max because the second derivative is positive, we can already cross that off. And this one here about having a relative min because the second derivative is negative, B is also a bogus answer right off the bat. So it's really immediately down to A or D. So we need to figure out the second derivative and plug 0 and -2 into it to see if it comes out positive or negative. So for the second derivative, well, here's the first derivative. Again, if you plug in 0, -2, we're going to get 0. But now for the second derivative, I'm going to need the quotient rule. So we have a 4x and a 9y, and I'm going to use the general format u prime v minus uv prime over v squared. I'm just setting that up in my box and ribbon here. So my derivatives, I've got 4, and derivative of 9y, I'm implicitly differentiating y as an inner function of x. So this is going to be 9 dy over dx. And then if I plug 0, -2 into this, right inside the box, also including the first derivative value of 0 that we found here, then that's going to be, let's see here, 4 times 0 is 0, 9 times -2 is -18, 4 is just a constant, and then this is 9 times the derivative 0, which is also 0. Multiplying this out, we've got 4 times -18, which is -72, minus 0 times 0, which is just 0, all over -18 squared, which is, well, let's see here. This is a no calculator question. So 10 times 18, that would be 180. And 8 times 18, let's see here, that would be 80 plus 64 is 164 plus another 180. So that's going to come out to 324 when all is said and done. So we've got -72 over 324, and you could keep reducing this all day if you wanted to. I mean, we can call this, let's see, -32, or 36 rather, -36 over 162, and then this can be reduced further to, let's see here, 2 over 9 eventually. For this problem, we're given the point 0, -2 on the curve C, and also the first derivative, 4x over 9y. We want to know which of these statements is true. These are all talking about whether the curve has a relative min or max at 0, -2. And if you look at all these answer choices, these are all using the second derivative test, where the first derivative is 0 and the second derivative is either negative or positive, and that helps us decide. So let's start by actually taking the first derivative. I mean, if you look at these answer choices, the first derivative comes out to 0 in all of them, but let's just make sure. So if I plug 0, -2 into 4x over 9y, that's going to be 4 times 0 over 9 times -2, which is 0 over -18, which is 0. So that's definitely true. But now we're going to have to figure out what the second derivative looks like. So for that, I'm going to use the quotient rule. So we've got u prime v minus uv prime over v squared. To help me organize that, though, I'm going to use the box and ribbon here. So we've got 4x as my numerator, 9y as my denominator. Derivative of 4x is going to be 4. Derivative of 9y is going to be 9 times dy over dx. 9 is already an inner function of x, so whenever we take its derivative, using implicit differentiation, we have to multiply it by the derivative of y. Okay, so before I multiply this all out and put it back together, let me plug in the point 0, -2 along with that derivative that we just found of 0. So putting this inside the box, and then I'll just assemble it outside here. We've got 4 times 0, the x value 0, that's going to be 0. 9 times the y value negative 2 is negative 18. And then we have 4 is just a constant. 9 times the x, or the dy over dx value 0 is going to be 0. Multiplying it back out. So now this is the second derivative evaluated at 0, negative 2. We've got a fraction. And on top, we've got u prime v. That's going to be 4 times negative 18, which is going to be negative 72 if we multiply that out, minus 0 times 0, which is just 0, all over 18 squared. Well, let's see here. What's 18 squared? We've got 8 times, well, let's see, 8 times, 20 times 18. Let's do 20 times 18 and then subtract 36 from that. So that's going to be 360 minus 36 is going to be 324. And we have to do it this way because there's no calculator allowed on this problem. All right. So without doing any further math, we can conclude that this is negative, which is a good thing. But if you wanted to, you could certainly reduce this. I mean, 72 over 324, that reduces by 2's to 36 over 162. And 36 over 162, that reduces to 18 over 81. And that reduces by 9 to 2 over 9, and this whole thing is going to be negative. At the end of the day, though, one way or another, we've got a negative value, which means by the second derivative test, we have a relative max at 0, negative 2. So looking at our answer choices, we have a relative max because the second derivative is positive? No. Because the second derivative is negative? Yes. Choice D. For this one, we have a second derivative given by this function, and we want to know at which of these values do we have a point of inflection for the original function. So I need to find some critical values and do some sign analysis. I need to know where f double prime here is changing sign. So let me set this equal to 0. And this is going to equal 0 if x is 0, 3, or 10. Let me set up an f double prime number line now and put those critical values on there. So we have 0, 3, and 10. And now let me test something to the left of 0, like negative 1. So plugging it into the f double prime here. Now this x minus 10 squared business, because we're squaring it, it's always going to come out positive. So we actually don't even need to look at that when we're doing sign analysis. It's just going to be all about the x and the x minus 3 to the 5th. So if I plug negative 1 in, I've got a negative times another 5 negatives, an odd number of negatives. That's going to come out to a positive. Next, a number between 0 and 3, like 1. That's going to be a positive times a negative, so negative overall. And then between 3 and 10, 4 works, so does 9, anything in between. So that's a positive. Positive comes out positive. And then after 10, we've got, how about 11? That's going to be a positive times another positive. So that's also positive. So we see here that f double prime is changing signs at 0 and 3. Therefore, f has points of inflection at x equals 0 and 3, giving us choice B. On this problem, I'm given the second derivative of a function, this crazy-looking function here. This is a calculator problem, in case you were wondering. We want to know at what values of x between negative 4 and 3 does the graph of f, which they did not give us, have a point of inflection. So I need to know when f double prime is changing sign. And to see that, I'm just going to graph this on my calculator and see where it crosses the x-axis. So here we go. So here I am in my y equals. I've entered this function in here using my fancy fraction, alpha y equals n over d form to get that nice little fraction in there. And now I'm going to go to window, and I'm going to set my window to be from negative 4 to 3 because that's the interval that they gave me. And let me do zoom 0, zoom fit, to see what f double prime looks like across that interval. Now again, we're looking for sign changes. So there's not a sign change, that's actually a bounce. This is a sign change over here. We're crossing the x-axis here. So we've got second trace 0, option 2. Let me move my spider a little bit closer to that intersection and press enter. Press enter a little bit to the right of that. Press enter one more time, and that's going to come out to about 2.229 when all is said and done. Now, I'm guaranteed based off these answer choices that I don't have multiple points of inflection other than this one, because you might be thinking, well, this spot here, how do we know that we're not like dipping a little bit below and then coming back without zooming in? Well, if that were the case, that would be 2 more points of inflection. So then we would have an answer choice with 3 of those, and they didn't give us that. So presumably this is the only point of inflection, and what looks like a bounce really is a bounce. So therefore, f has a point of inflection at x equals 2.229, giving us answer choice A. For this problem, we're given the graph of f prime, and we want to know basically how many extrema and points of inflection the graph of f is going to have based off of what we see here. So for extrema, we're going to have an extreme anywhere that f prime is changing sign. So f prime is going to change sign in how many places? Well, we've got 1, and let's see, this jump counts as a sign change, so that's 2. And then this x-intercept is a third, so that's 3 times, giving us 3 extrema on the original graph. And now for points of inflection, that's going to happen wherever f prime changes from increasing to decreasing or decreasing to increasing. Basically, whenever f prime is reversing direction. How many times does that happen on this graph? So we're going up and then down, so there's 1 right there. Here's another direction reversal, so that's 2. Let's see, here we're increasing and then decreasing, that's 3. This is decreasing to decreasing, that doesn't count. Down here we're reversing direction, that's 4. So 4 total, giving us 4 points of inflection on f. So we've got 3 extremes and 4 POIs. That's going to be choice C. On this problem, we're given the second derivative graph of a function that's continuous. And let's see here, we're told that this function has one critical point, only one critical point on the interval from 0 to 9, and that happens at 6. Based on that, we want to know what's true about that function. So these answer choices are all about whether we have a relative min or max and whether we also have an absolute min or max. So let's deal with the issue of min versus max first. So we already know that we have a critical value at x equals 6. And since we have the graph of f double prime, we're just going to use the second derivative test to see if that critical value is a max or a min. Looking up what's happening with x equals 6 on the graph, we see that f double prime of 6 is a positive number. That means by the second derivative test, we have a relative min at the very least. Now, the million-dollar question is whether this relative min is also an absolute min. To help us with that, they told us that f has only one critical point. Since x equals 6 is the only critical point, and there's basically no other place to turn around, that means that until you get to x equals 6, your function is decreasing, and after 6, your function is increasing. So this x equals 6 must also be the absolute minimum for the function on this interval. So that's going to be choice B. On this problem, we're given the second derivative of a function, and they're telling us that 2 of the critical points are 0 and this other crazy decimal. We want to know which statement is true about those points. So they're telling us that we have mins or maxes, local mins or maxes at each of these. We already know that they're critical points, so really we just have to plug these 2 points into f double prime and check out the sign to see if we're dealing with mins or maxes. We're just using the second derivative test here. Because this is a calculator question, I'm going to enter this function on the calculator and enter these points into the function. Let's do that now. So I've entered this function in my y1. I'm going to quit out of there now and do alpha trace to pull up y1. And then let's see, parentheses, let me plug in 0 first. Comes out to -2 exactly, and I probably didn't need the calculator to see that, but there it is. So since that comes out to a negative number, this proves that f has a relative max or a local max at x equals 0. Next, let's try f double prime of 6.949. So back to the calculator. Let me yank that input from before, and instead of 0, I will plug in 6.949, which comes out to roughly -1.817. Now, again, the important piece here is that this is a negative number, so that says that f also has a local max at x equals 6.949. So that's going to be answer choice D, max for both. On this problem, we're given that f is a continuous function on the interval from 0 to 9. So at the very least, that means the function exists everywhere on that interval. And it's twice differentiable except at x equals 6. They also gave us a table here of all of the, well, at least a few of the f primes and double primes and their signs on this interval from 0 to 9. So based off of that, we want to know which of these statements here could be false. So that means there are 3 true statements and 1 false. All right, so let's go through each of them and see what's true and what doesn't have to be true. So statement A, function f has a relative max at x equals 2. Well, let's look at x equals 2 and see what's happening. So we see here that we have a 0 value for f prime. F prime of 2 is 0. And f double prime of 0 is negative 1, which is a negative. Well, based off of the second derivative test, this means you have a relative max at x equals 2. Moving on to x equals 4, because choice A matched up what they said it should. Choice B, point of inflection at x equals 4. Okay, so for a point of inflection, we're looking for either 0 or it does not exist for f double prime of 4. And we've got f double prime of 4 is 0, so that's good. And we also have a sign change at x equals 4 from negative to positive. So really the sign change is also the big key for this point of inflection. No sign change, no point of inflection. But we see a sign change here. So we can conclude we do have a point of inflection at x equals 4. Next, we have a relative min at x equals 6. Well, we don't know anything about the derivatives that would be useful here, but what we do know is that f prime is changing from negative to positive at x equals 6. Therefore, f must have a relative min there. That would be the first derivative test. And then finally, and so it's looking like D then is the only one that hasn't been proven to be true. The graph of f has a point of inflection at x equals 8. Well, we do have f double prime of 8 being 0, which is good, but we're changing from negative to, we don't know. Well, this is an issue. Since we don't know that f double prime changes sign at x equals 8, I mean it might not, that means that we may not have a point of inflection at x equals 8. Or we may, but we can't prove it. And that's really what this question is getting at, is what statement could be false. So that would be then choice D. On this problem, I'm trying to figure out which of these functions I can't use the second derivative test to show that x equals 2 is a min or a max. So I've got the original functions, I've got all the f primes. I'm going to have to supply the f double primes later on, but let me start with the f primes. So if the second derivative test is going to work, then f prime of 2 is going to have to equal 0. Let's just actually plug into all these to make sure that's the case. So if I plug into here, sine of 0 is 0, so that works out. If I plug into this one, we've got e to the negative 1 minus, let's see, the 1/2 and the 2 cancel, so it's really just minus e to the negative 1 again. That comes out to 0. Down here, 2 times 2 minus 4 is 0. And here we have 3 times 4, which is 12, minus 24 is negative 12, plus 12 is 0. So for all of these, f prime of 2 does equal 0. So let's move on then to the second derivative. Second derivative for the function in A is going to be negative cosine of x minus 2. And if I plug 2 into that, this is going to be, let's see, cosine of 0 is 1, but it's negative, so that's negative 1. A negative value for the second derivative means that we have a relative max. So second derivative test works on choice A. Now for choice B. Well, this is a little bit of a beast, but let's go ahead and take this derivative. So this is going to be a chain rule for this first term. We have negative 1/2 e to the negative x over 2. For this next one, we have a product rule. So I'm just going to do u prime v minus or plus uv prime. I'm not going to worry about the box and ribbon on this one. So then let's do u prime v. That's going to be derivative of the first thing times the second thing. So that would be negative 1/2 times e to the negative x over 2. And then we have uv prime, that's the first thing, which is negative 1/2 x, times the derivative of the second thing, which is negative 1/2 e to the negative x over 2. We have a negative 1/2 times a negative 1/2. That's a total of positive 1/4 with an x and an e to the negative x over 2. So kind of a pain, but it is what it is. At this point now, let's plug in 2 to this expression. And when I do that, I can actually combine these two terms here. So this is going to be just negative e to the negative x over 2. So when I plug in 2, I can just write negative e to the negative 2 over 2. And I've got this other function here. This is going to be 1/4 times 2 times e to the negative 2 over 2. All right, well, what's this mess going to come out to? So we've got, this is negative e to the negative 1. This is 1/2 e to the negative 1. And it looks like actually, so we have a 2 down here. We can move this, so this actually is going to be negative 1 over e plus 1 over 2e. So basically we've got a negative 1 over e, and then we're adding half of a 1 over e. So that gives us a negative half of a 1 over e, basically, or negative 1 over 2e. In any case, this is a negative value, so that means we have a min, a local min, based on the second derivative, local max, rather, on the second derivative test. So that means the second derivative test works, because this either comes out negative or positive, specifically negative. Fine. Moving on to the next one. Second derivative here is quite a bit easier. It's just 2. No matter what you plug into it, it's always going to be 2. Since that's a positive value, that means we have a local min based off of the second derivative test. And this last one, we've got 6x minus 12. If we plug 2 into that, 12 minus 12 is going to be 0, which doesn't tell us a whole lot with the second derivative test. So choice D is the only one second derivative test does not work on.